Greetings, Math 243 students, and welcome to the binomial distribution. Very exciting day. All right, let's go ahead and get started talking about the binomial distribution. So the binomial distribution is just a special type, a very commonly used type of a discrete probability distribution function. So what we learned about in 4.1 and 4.2 is all going to apply to the binomial distribution. This is just a special one that we use a lot. For this one, we're going to do a number of trials of an experiment. Each repetition of the experiment is exactly the same as the previous one. Nothing changes between the trials. And the letter N is going to denote the number of trials that we do. In this type of experiment, there's only going to be two possible outcomes. You're either going to have a success or you're going to have a failure. So the letter P is going to denote the probability of a success, and the letter Q is going to note the probability of a failure. And note that, of course, P plus Q would equal 1 because they're complements. And the N trials in the experiment are going to be independent and repeated using identical conditions. So there's nothing going to change between the trials of the experiment. All right, so let's look at some examples. Maybe we're going to flip a coin a whole bunch of times in a row. Each coin flip is a trial of the experiment. If it's a fair coin, it would be 50% chance of success. And the number of trials depends on how many times we want to flip the coin. Another example would be if you're taking a true-false test and just guessing the answer. The number of trials would be the number of questions on the test. Each question you guess with a probability of success. Basically, anytime there's going to be two outcomes in a series of trials, and one could be thought of as success and one's failure, it's going to be the binomial distribution. Let's talk about the notation just a little bit. Remember, the binomial distribution is going to be a distribution on a random variable. We use capital X. And in this case, X is going to be the number of successes obtained in N trials. Okay, that's always going to be X for the binomial distribution. Again, N is the number of trials, P is the probability of success, and Q equals 1 minus P, the complement of success, which is failure. A little bit more notation. Oftentimes you'll see binomial distribution represented with the notation B, NP. So the B is just to indicate that this is a binomial instead of like a Poisson or a geometric or other things we're going to talk about later. B, and then N is going to be that N up here, the number of trials, and P is the probability of success. And of course, we don't need to write down Q because we can quickly compute it by subtracting P from 1. All right, so let's just do an example, making sure we understand the setup here. So a trainer is teaching a dolphin to do tricks. The probability that the dolphin successfully performs a trick is 35%. And the probability the dolphin does not perform the trick is 65%. Out of 20 attempts, we want to find the probability that the dolphin succeeds 12 times. So first, what is our random variable here? What are the values of N, P, and Q? And let's finish the notation. Why don't you pause the video and see if you can fill these things in for yourself? All right, are you back? Well, X, the random variable, is the number of times the dolphin successfully performs a trick. Remember, that's always going to be the flavor of our random variable for binomial distribution. The number of attempts was 20, so he tried the trick 20 times, or she. The probability of success was 35%. The probability of failure was 65%. And if we wanted to write this in binomial notation, we'd write B 20, 0.35. I'm not going to answer this question right now, but you can come back to this later and figure it out. In just a few minutes, you'll be able to do this. All right, so let's do another example. Let's say we're going to flip a fair coin 15 times. Each flip is independent, and we want to know what is the probability of getting more than 10 heads. Again, X is going to be the number of heads because we're going to call getting heads a success. Now, you wouldn't have to do this. You could call getting tails a success, but we all just need to agree on something. So we're going to say that getting heads is a success. It's going to take on the values 0 through 15, so N is equal to 15. And since the coin is fair, it's going to be 50% for P and 50% for Q. All right, so we're going to go to Excel and learn how to calculate these probabilities. So go to your MyOpenMath page, and I will show you where that is. So here's our MyOpenMath class. Go down to week 4. And here's the Excel file you're going to need is going to be under the 4.3 video lecture notes. Here's the Excel file. Download that guy. We don't need this anymore, so let's move that out of the way. And oops, I do need to close this though. And open the Excel file. And here it's popping up. Enable editing. And this looks pretty good, except for you can see that this column title is cut off. So right now, let's just adjust the width of this column so we can see that full thing. There we go. That looks nicer. All right. So a fair coin is flipped 15 times. This is what we were talking about. Each flip is independent. What I have here is the probability distribution table for this binomial experiment. All right, here's my number of heads, and the heads can range from 0 to 15. I could get no heads, and I could get 15 heads. All right. Here is the probability of getting exactly that number. So that means x equals x, means the number of heads equals the data value 0 or 1 or 2 or 3, etc. And that's filling in this table. So if I want to know the probability of getting exactly 5 heads, I can go here to 5. That's the number of heads. And here's the probability of getting exactly that number. All right. So we can actually just type that in here. We answered one question. 0.0916. That's enough for me. So I wanted a little bit more. Nope, wrong way. I always do that wrong. All right. The last column is called the cumulative distribution function, and what it tells you is the probability that the random variable is less than or equal to the data value x in that column. So what does that mean? Well, for the first one, it means the same because you can't be less than or equal to 0 in this distribution. 0 is the smallest. So these two guys are the same. I think this one's just a little bit wider. They're exactly the same as you look at them spread out. But when you get to the next one, this is giving you the probability that the random variable is less than or equal to 1. So to be less than or equal to 1, that means you're either 0 or 1. So this adds 0, probability of getting 0, and the probability of getting 1, and it puts it into this value. So if we want to know the probability of getting, I don't want that to say exactly, well, whatever, exactly 5 or fewer heads. So we want 5 or fewer. So we want the probability of 0 plus the probability of 1, 2, 3, 4, and 5. One way we could do that is we could just add these values up if we wanted to. Or we can use this second column and we can say that this is the probability that the random variable is less than or equal to 5. So we can put in 0.151. 0.15, am I doing 4 decimal places? 09. Didn't quite fit. Let's make it a little bit bigger. All right. What is the probability of getting 12 or more heads? All right. So we have to think about this one a little bit. Okay. The probability of getting 12 or more, there's two ways you could do this. You could do 12 plus 13 plus 14 plus 15. That would be 12 or more heads. Or what you could do is you could do 1 minus the probability of getting less than 12 heads. Okay. So that would be 11 or fewer. So there's two ways. Way 1 equals, add them all up. Okay, so I'm going to do way 1 right here. This is equal to, and I'm just going to use a little bit of a sum. So this guy plus this guy plus this guy plus this guy. All right, perfect. That's the probability of getting 12 or more heads. Way number 2 equals 1 minus the probability that x is less than or equal to 11. Right? So 12 or more, that's going to be all these. The opposite of those would be 11 or fewer. And that number is right here. So let's put that one in. So it would be equal to 1 minus 11 or fewer. And luckily, or thankfully, and it turned out the same way either way you did it. All right. I'm going to move this one down just a little bit because I don't like it there. I just copied and pasted it. We'll come back to the expected. Actually, let's go ahead and do the expected number of heads right now. How did we compute expected value for probability distribution functions? Well, we took each value of the random variable times its probability. So this would be equal to 0 times 3.05 times 10 to the negative fifth, 1 times 0.0004578, et cetera, et cetera, et cetera. 2 times this number, 3 times this number, 4 times this number. There's a really slick command in Excel called sum product. And what it does is it takes in two arrays and does exactly what we want it to do. Multiplies the first value in the first array times the first value in the second. Adds to that first value in this first column, or second value in the first column, second value in the second. So let's give that one a try. Equals sum product. You could just do this by hand. And it takes array. So we want the sum product of the value 0 through 15, comma, their probabilities. And this function knows to take 0 times this, plus 1 times this, plus 2 times this, all the way down to 15 times this. End our parentheses and hit enter. And we get the expected value using our way of computing expected value as 7.5. All right, so this is using a binomial probability distribution table. But the question next is, how can we create a binomial probability distribution table? Well, let's go ahead and look and see what we have plugged into these different cells. So let's go ahead and look in here. You'll see right up here, it says binom.dist, and then it has some different cell references, okay? The first thing it has is A6, which means a 0. The second thing it has is a 15 because the coin is flipped 15 times. The third argument is the probability of a success. And the final argument means, do you want cumulative or not cumulative? Remember in this column, this was just x equals particular values, not accumulating things. So we have that set to false. If we look here, the only difference between these two was that this is set to true and it's going to accumulate these values. All right, so this is how we use the binom.dist function in Excel. The first argument is the number of heads you want, number of successes out of how many trials, the probability of success, and whether you want it to be cumulative, like this column, less than or equal to, or not cumulative. Let's practice using this Excel function. Let's go to the second tab. Let's do an unfair coin. So I have this all set up for you guys. And the thing is, it's almost exactly the same experiment, except for that this time our coin is unfair. And the probability of getting heads is 70% instead of 50%. So in this value, we're going to go equals binom.dist, our binomial distribution function. We're going to start figuring out the probabilities. The number of successes, I'm going to do a reference to this cell over here that has my 0. You could just type in a 0 if you wanted to. That would be fine. This way I can copy and paste. Comma, the number of trials, that's 15. The probability of a success is 0.7. And remember, in this column, I don't want it to be accumulating. I just want the discrete value, so I'm going to put false for accumulative. So binom dist, a reference to the number of heads, 15 successes, 70% chance of success, and not cumulative. And I hit enter, and it gives me the probability of getting 0 heads on 15 coin flips. Now, the nice thing about making this reference to A6 is now I can just drag this formula down and the reference is going to update. It says to Excel, oh, hey, when we're doing this distribution function, instead, look to the cell just to the left. I'm in B6, but look to the one just to the left for that first value. And you'll see if you look at any of the other cells, this one refers to A10 just to the left. This one refers to A14 just to the left. All right? Let's go ahead and fill out the cumulative function. So this equals binom.dist. Again, I'm going to refer to this time the cell 2 to the left, but it's still just A6. 15 trials, 70% chance of success, and true, because I want it to accumulate. And I'm going to copy and paste that guy down just by dragging this down. And it fills it up. And luckily, it equals 1, so we feel pretty confident about this being a real probability distribution. Because remember, we needed those to add up to 1. All right, I want you to pause the video right now and answer these questions using your probability distribution table. All right, were we able to do this? What is the probability of getting exactly 5 heads? Well, here's 5 heads. So here's the probability of getting exactly 5 heads. And I'm going to be lazy. I'm going to type equals. I'm just going to refer to that cell. Maybe I'll make this one a little bigger so we can see a few more decimal places. Oops, wrong one. There we go. What is the probability of getting exactly 5 or fewer? So this one, we want to add 5 or fewer so we can look at the cumulative fun. 5 or fewer, is that going to be that guy? What is the probability of getting 12 or more? Remember, there's 2 ways to do this. You can add up 12, 13, 14, 15. That's way 1. Or you can equals 1 minus 11 or fewer. And finally, what is the expected number of heads? Well, we're going to do our sum product. And the values of the probability distribution table multiplied by their own probabilities. And this time, the expected number of heads is 10.5. All these probabilities, well, not all of them, but the probability of getting 5 or fewer heads is probably less than before because we had a 50-50 chance before. Now we have a higher chance of getting heads, so getting fewer heads is less likely. And in fact, the expected number of heads now is 10.5, whereas before it was 7.5. We're going to come back to this, so keep that in your mind. All right, so one last page of examples. We don't actually have to scroll up to the top here. You don't actually have to build the entire probability distribution table to answer questions using the binomial distribution. So let's do a couple practice problems like this. 30 people were exposed to a virus. The probability of catching the virus is 45%. What is the probability that exactly 15 people catch the virus? So exactly 15. So we can use binom dist to help us calculate this. Equals binom dist. And, oh, I think I forgot my dot. I don't think it matters that much, but I'm going to put it in there just to be, I don't want to see this. Okay, binom dist. And we want to know what's the first value that we put into binom dist? Well, that's going to be the number of successes. And that would be, in this case, catching the virus. You may not feel like that's a success, but that's what I'm defining a success to be. Out of 30 trials, 30 people were exposed. The probability of catching the virus is a success is 45%. And we're going to set this to be false because we want to know exactly 15 people catch the virus. So 12.4% or 0.124 is the probability exactly 15 people catch the virus. All right, what is the probability that at least 15 people catch the virus? So 15 or fewer. 15 or greater, right? Sorry, at least 15 people catch the virus. So this is 15, 16, 17, all the way up to 30 people catch the virus. So remember, this is going to be the same as 1 minus the probability. Oops, I can't type probability that 14 or fewer catch the virus. Okay, so this is going to equal to 1 minus binom.dist. And 14 or fewer would be 14 out of 30, 0.45% chance of catching it. And we do want cumulative this time because we want to know the probability that 14 or fewer catch the virus. So a 35.5% chance that 14 or fewer people catch the virus. What is the expected number of people to catch the virus? Well, we don't have the probability distribution table built for this one. We could build it and just do the sum product. Or we could also do this new slick formula for expected value of a binomial distribution. I haven't told you this yet, but it's actually going to be P times N, okay? So the probability of success times the number of people in the trial. So in this case, this is equal to 0.45 times 30. So we expect 13.5 people to catch the virus. And we'll come back and talk about that again. All right, I would like you to pause the video and I would like you to try number 2 right now on your own. All right, let's look at this problem. A baseball player has a batting average of 0.165. What is the probability that he hits exactly 1 hit in his next 7 at-bats? So a success is going to be a hit. The probability of a success is 0.165. So this is a binomial distribution problem because he's either going to hit it or he's not going to hit it. Equals binom.dist. Number of successes. Well, in this case, we want to know if he gets exactly 1 hit out of 7 at-bats. The probability of success is 0.165. And we do not want cumulative. We just want to know exactly 1 value. So I want false. Exactly 1 value. So he has a 39.1% chance of getting exactly 1 hit in his next 7 at-bats. All right, one more story problem. The probability that the Springfield Isotopes will win any given game is 0.3897 based on their 13-year win history. An upcoming schedule contains 25 games. So again, this is binomial because they're either going to win or lose, success or failure. And we know the probability of success is 0.3897, and they have 25 trials. All right, so pause the video and compute A, B, and C for this one. All right, are you back? Awesome. What is the probability they win exactly 10? So that's binom dot dist 10 out of their 25 games, 0.3897, comma false, because we want to know an exact value. 16% chance they win exactly 10 of the next 25 games. And don't forget that if you need more decimal places to enter your answer, you can always spread out that column to see a few more decimal places. Find the probability that they win more than 11 of the 25 games. So that would be 12, 13, 14, all the way up to 25. So you could add those guys up individually, like compute 12, compute 13, etc. Or remember, this is the same as 1 minus the probability of a winning less than 11. So that would be winning 10 or fewer games. Right, more than 11. Oh, no, I'm sorry, more than 11. So that would be the 1 minus of probably winning 11 or fewer. Right? You got to read that really carefully, and I didn't. So the probability of winning more than 11 games, that'd be 1 minus the probability of winning 11 or fewer games. So this is equal to 1 minus binom dot dist of 11 out of 25 with a 0.3897 chance of success. And we do want the cumulative because we want to know 0, 1, 2, all the way up through 11 games. Right? So that's going to be 0.234, that they win more than 11 of the 25 games. And finally, the mean of the distribution, I just told you this formula now. Remember that it's n times p. So it's going to be equal to 0.3897 times 25. Probability times the number of games. So we expect them, or the mean is going to be that they win 9.7 games. All right, so Excel's really handy for letting us calculate binomial distributions. All right, coming back to this slideshow, we have a few more things to talk about. We did this in Excel. I did this a little bit in Excel, but I want to review this for you now so you have this written down carefully. For a random variable binomial distribution, and with all these definitions that we had before, the mean, variance, and standard deviation can be computed the following way with these formulas. The mean is equal to the number of trials times the probability. The variance is equal to the number of trials times the probability of success times the probability of failure. And as always, the standard deviation is the square root of the variance. So you are able to calculate those using these formulas. All right, so let's go ahead, and we did this before just in Excel, but let's calculate this by hand. What is the expected number of wins? We're going to use mu equals n times p. So in this one, that's going to be 25 times 0.3897, which I actually have a calculator here today. 25 times 0.3897. Oops, I pushed the buttons wrong though. 25 times 0.3897 is equal to 9.7 games they think they might win. And what is the standard deviation of the number of wins? That's going to be sigma, and that's equal to the square root. Remember our formula right here. Sigma equals the square root of npq. N times p times q. So that's the square root of 25 times 0.3897 times 1 minus 0.3897, which is 0.6103. Using my calculator to compute that product and then take the square root, I take 25 times 0.3897 times 0.6103, and I get the square root of 5.9458, and that is about equal to, where's my square root button on this guy? 2.44. as my standard deviation value. All right, well, that's it for binomial distribution. And good luck with this one. It's a fun one.